Okay, it looks like the stream is working. I'm going to give us a second, hope that it actually is. Okay, it looks like the stream is working. I'm going to give us a second, hope that it... Yeah, that's what happens when you forget to mute the second computer. Okay, I'm not quite sure why OneNote doesn't want to be full screen, but it's not going to kill us. Can you guys hear me? Okay, thank you for confirming. If I do anything that causes a lot of extra noise, let me know, because I kind of have the microphone next to me, so I'm not sure if it'll cause a lot of banging with the coffee table I'm at or anything, and I don't want to deafen anybody. Okay, so at this point, everybody's taken, well, I'm not quite sure if everyone has taken exam two. I'm sure you all realize there was some oddity due to a hurricane. So there were people who had to reschedule. Let me see if I reorient my screen, if it fixes anything. I don't think wearing headphones will be a problem, but I'm a little paranoid that I'm going to bump something and terrible things will happen. Okay, I'm trying to figure out what is up with this screen focus. This did not happen last time I used this software. This is annoying. See, maybe if I swap it back into desktop mode. I'm pausing for a sec so I can see what it changes. Everything that pops up on YouTube is like 30 seconds behind what I'm actually doing. Oh, okay, thank you, Brian. I had thought there was one person left, but I guess we must have got him when I wasn't looking. Okay, I'm sorry about the blurry. I'll try to figure it out for next time, but I don't want to waste your time sitting here screwing with it for too long. And you guys have copies of these problem sets, so if you can't see something that he's written, that should work out okay. So everyone's taken the exam, and you can talk about the exam. We are currently grading the exam. A couple of problems are being actively graded, and there's one where we're still tweaking the rubric a little bit. If you're kind of curious about that process, we attempt to keep correctness and clarity separate because we don't want a situation where someone getting the problem wrong means that they lose all the clarity points too. And we also try to roughly have it so that if you at least know what a problem was doing and you make some kind of credible effort, you at least get a 1. And then a 2 is something in the ballpark of you mostly had it, but there's a serious problem that makes us not feel good about giving you 3. And a 3 is kind of around, yeah, you knew it. Maybe there's a couple of little issues, but given more time or given an opportunity to edit, I'm confident that you had this. So that's the rough rubric for every problem, but since we have 2 TAs per problem grading, we have them work together to come up with something a little more concrete for the nature of the specific problem they're working on, so that they can do a better job of being in sync and coordinating themselves, so that the grade you end up with doesn't depend on which person graded it. And I'm sure some people are also curious about what happens when you challenge a grade. In that case, our first step is to have the second grader, the person who did not grade your problem originally, take a look at it. And so that way you get a fresh pair of eyes on it. But we only change a grade when it's clear that the original grade was objectively wrong. Like, as a true example that comes up periodically, if you took several pages to write an answer and we missed one of the pages somehow, because when you're going through 150 PDFs, sometimes you're going to think someone finished on page 2 and they actually had a page 3 or something like that. And so we say that a step was missing, but you can say, no, if you looked at the next page, it was there. And then we say, oh, I'm sorry, we didn't need to do that, we'll fix it. Or on rare occasions, someone takes an approach to a problem that we never saw coming. And at first we think it's wrong, but then we realize that there's actually a valid point in there and it should have gotten points. But what we don't do is give additional points if someone's just saying, I kind of think you should have given me more points for this, so look at it again. You have to be able to give us some kind of reason. And we try not to make it so that we casually change the grade, because we don't want a situation where everyone is asking us to review every single problem just in case we might give them another point. It's a tricky balancing act because we want to be fair, but the more time that we put into that kind of thing and the reviews and all of that, the less we have to try to help you with new material, and everything kind of piles up and gets completely out of control. So we do our best to balance it and to do it in a way that's good for everybody. So if you've ever been curious about the logistics, that's about where we are. I really don't think the grades will be out by tomorrow. I think that was the original target to finish, but a couple of things have happened on campus that have slowed things down here, so I think it'll be a couple extra days. Anyway, during the exam period, someone posted a private message with the excellent point that if you don't read a question correctly, you're completely hopelessly lost and you're never going to be able to get it right. And so they were asking for advice on how to read the questions during the exams. I didn't really want to give someone private advice on that in the middle of an exam because it seemed unfair to the class. So I said afterward I would double back and dwell on that a little bit more. Clearly, when you're faced with these gigantic equations, it's easy to get overwhelmed. If you're a math major in your past life, probably you're okay. Probably this is not that helpful to you. But for those people who haven't seen math in 10 years or 20 years, it's easy for how condensed this information is to become completely overwhelming. So as the first piece of general advice I'd give, and you may have seen when I wrote my problem set answers a couple of times, I personally tend to tackle problems by reading through and picking out any piece of information that I feel I actually understand. Like, if it's one of these problems that talks about doing a hash of an n-bit string, then I would at least say, okay, I know that there are strings involved and the strings have n bits. So it's not a big place to start, but it's something. And then the next piece of information that I actually understand, I might scribble right under that. And I add little chunks and build them out. because I personally don't do very well if I try to just read the whole problem at once and figure out what the whole thing is. I do better with a kind of dynamic programming approach where I figure out little things and then I piece my little things together and eventually I get there. So let's see. I wanted to talk a bit about, I believe this is problem set 7, number 3, because ordinarily by the time we reach this part of the course, this very similar problems to this, possibly this actual problem, have been used in past semesters. But ordinarily by the time we reach this point, we've done a lot of other stuff that involved set notation and sets and reasoning about sets, because that's important in the computability and complexity section. And it didn't occur to me initially when we were picking this out that it hadn't been seen quite as much this semester, and we hadn't really gone over it. So if you're curious about how sets work, the CLRS book talks about it. But I think for the people who have a lot of programming background and are much more comfortable with the programming angle, I would suggest looking at the Python implementation of sets. Python sets are very similar to math sets. They're just an unordered collection of things, and each thing can only be in there once. So, for example, with this sum set problem, you can actually pretty easily write a Python program that consists of a couple of for loops that implements this and finds what the sum set is. And one of the things you'll notice if you implement that is that even if you don't program in some kind of protection against having the same value get into the set repeatedly, if you're using the actual set type implemented by Python, it'll just drop it on its own. So you can try to put the number 2 into the set as many times as you want. And Python in the background will say, oh, I already have that, I don't care, and drop it and move on. So this is a prime problem for going back to a little Python interpreter and playing with it, if that's something that you think would help you to understand. You could also easily do this with, oh, thank you, Dan. Dan has pointed out that Java sets do the same thing. I am not a good Java programmer, so never ask me to help you with your Java homework, but Dan is a Java genius, so always go to him instead. So talking through this problem a little bit, mathy things fly at you. It says, given 2 non-empty sets of integers a and b, and you can just pause there for a sec and make sure you understand this much and say, okay, non-empty. That means we're guaranteed that neither of these sets is going to be completely without elements. And that's important to the end result because it's kind of nonsensical to even try to compute sums when one of your values is completely missing. Oopsie. I still have Slack running. Okay, anyway. So you have 2 sets, A and B. A and B are each just a collection of integer values. And because these are sets, you know that each integer value can only appear one time in each one. For the sake of, in case it ever comes up, if you are asked something about a multiset permits a value to occur more than once. But anytime you see the word set used, and it's not specified as some particular special type, then each value just one time. So we're defining the sum set, A plus B, to be, and these little curly braces are the standard way of indicating that we're building a set. That's all those mean. So for each member of the set, let me get an actual pen. This means the value A is in the set A. That means the value B is in the set B. You definitely want to know what this symbol means. That symbol will come up all the time in the later part of the course. And it basically just means it is in, it is a member of. So the sum set A plus B consists of the set of members where you can create values A plus B where come from the result of adding some member of A to some member of B. And then if you don't feel completely sure that you understand what that means, you should go down here to the example. And you can ignore the R values temporarily and just make sure that you understand why doing the sum set of this particular A plus this particular B results in that set. You really don't want to try to move on to doing any more special reasoning until you know you have that much, because everything else relies on this foundation, that you fundamentally understand what kind of situation the problem is trying to talk about. And this, I guess in both Python and Java, this could be very easily implemented by a pair of for loops, where you say something like for I in set A, for j in set B, add I plus j to the sum set. Now moving on to the next part, it's describing a new value where it says, okay, you have an x that exists in the sum set, and we're going to denote the number of ways that you can get x with this equation. So if, for example, like I don't think that example below does it a ton, but if, say, both A and B were 1, 2, 3, so like we had A, oops, I shouldn't have started writing so high. And now you can see that we do forgive bad handwriting because mine is not great. Anyway, if you actually had this, then it's pretty obvious that when you add number 1 from A to number 2 from B, you're going to get 3. And when you add number 2 from A to number 1 from B, you're going to get 3. And so that number appears 2 different ways already. And in the actual sum set, that number will not appear twice. But we're creating a new thing here, or defining a new thing here, where we actually keep track of how many different times you produce the same value if you actually looped over the whole sum set. So what this mathematically is actually saying is that we're defining, this is just defining what this is going to mean in the future. And so this means we're building a set. I'll get to the bars outside of it in a sec. This is a pairing of values where, from the pairings of A and B, where the sum would be x. And then these bars outside denote a thing called cardinality. And I think there are videos way at the beginning of the Udacity version of the course that talks about cardinality. Cardinality just means how many are in the set. For example, cardinality of this one is 3. That has 3 members. Cardinality of this one is also 3. It has 3 members. This has 7 members. So I forget the word cardinality all the time for some reason, but it doesn't mean anything that's fantastically complicated. And then once you're that far, I would say it's worth your trouble to walk through quickly and look at this example set of values for the different R's. or for the different possible X's rather, that make sure that you are correctly understanding where each of these values come from. And that's all the stuff you have to understand before you can really approach the actual question. We, more so in the problem sets, we will sometimes have very complicated questions. We try to choose somewhat simpler things in the exams. And particularly when it comes to the exams, if I see something in a question that I'm very confident is going to be misinterpreted, we usually try to add some kind of clarification. There will be times where I'll see people make the same mistake, 20 people having the same misunderstanding of a homework problem. So I'll say, well, we're going to see the same mistake on the exam, and we should try to nudge them away from that. This semester, it's going to be a little harder on us to do that because we're not grading your homework. So I'm not directly seeing what kind of mistakes you're making as you go all the time, like on a personal level. I read your problem set attempts on Piazza, but it's not quite the same thing. So we will definitely try. If there are any specific things about the questions on the exam so far that you felt have been particularly unclear, I would appreciate people trying to point out perhaps where we can make something a little more straightforward. We don't want to completely get away from writing things in correct formal math. One of the reasons for that is that while it's difficult to understand this stuff when you haven't had a lot of practice, these expressions of the information are incredibly precise. So once you do understand what the equations and that kind of thing say, you can communicate very specifically about what you mean. Whereas if we express something purely in words, there's a chance that you're going to misunderstand in a way that's correct according to English. Oh, I'm getting some advice on what's up with the video feed. I am actually not sure where to change that setting. Would I change it on the YouTube side or the streaming software side? Because I currently have open broadcasting software running. Oh, okay, it's on your side and I'm streaming correctly. Oh, that makes more sense. Yes, thank you. It didn't even occur to me that I didn't redo my settings on the second computer when I assigned. The way I've organized this, I have the feed of the stream going from one computer, and I have a second computer sitting next to me that is in charge of letting me see what you guys are saying. So that way I don't have to worry about trying to separate two windows on a single screen and only stream one of them. Oh no, we are not restarting right now. So I get a little confused sometimes between the settings of one or the other. But anyway, we've gotten this far through. You guys should understand what a subset is now, I hope. Otherwise, please try writing some Python or a little bit of Java and playing with it. It should be like, 3 to 5 lines of code. It's not going to kill you. So we're going on, and part A, hopefully everyone has seen this notation, this half-open interval notation. That is also probably going to be a big deal throughout the rest of the course. Not necessarily specifically the half-open interval, but to pull this out, when you have an interval, Square brackets mean included. Round brackets mean not included. So for this particular half-open interval, it means that you start at 0, and 0 is allowed to be one of the values. And you go up to n, but n is not allowed to be one of the values. So for example, our a and b above, you could say that was over the half-open interval of 0 to 5, because every value is at least 0, but less than 5. But it's also would be perfectly valid to say that those were over the half-open interval, say 0 to 10, because you're at least 0 and less than 10. There's nothing in this problem that's calling for using every possible value that you're allowed to use. So what it's going to ask you to do is figure out exactly what the upper and lower bounds for the number of distinct elements in the sum set are. Now, by definition, it's a set, so there will never be two non-distinct values, actually. They couldn't exist in the set together, because that's just how it works. But you really can get exact values here. Every once in a while, in the past, when we've used this problem, people have tried to argue, like, well, no, I can't really know. When we're saying exact upper bounds and lower bounds, we're saying, like, what is this, for some given value of n, what would be the smallest possible sum set you could end up with? What would be the largest possible? And your final answer, because this is asking about sets over an interval that includes n, so n is a variable, your final answer has to be with respect to n. You can't come back and say, I'm going to say n equals 100, and here's the upper and lower bounds for n equals 100. That's my answer. That would maybe get 1 point for you could at least kind of see that you knew how the sets worked, but we couldn't give you much more than that, because it's a really big misunderstanding of how the problem was meant to work. You're supposed to express how the upper and lower bounds behave for an arbitrary value of n. And that is a mistake I see every time, every single time. I think this problem has been used 3 times. So I have a pretty good sample size on that, actually. And then it says, argue why no sum set will violate these bounds. So you have to actually give us some kind of, here's why I know it could never be smaller, here's why I know it can never be bigger. And when it says exhibit sets, that means you can actually pick out a set. Like at that step, because it says exhibit sets, it's okay to pick something. Here is a specific one that shows the lower bound is for real. It can actually happen. I'm showing you where it happened. Here is a specific one that shows the upper bound is for real. I'm showing you where it happened. And these bars are cardinality again. That's really, it's, someone was asking earlier about the content of the later parts of the course. I haven't yet seen the actual problem sets or exams, but historically, stuff like set notation and cardinality and the in symbol and that sort of thing have been reused a lot. So I would anticipate that you will see them many times. The sooner you make a point of drilling that into your head as best you can, the more pain it'll save you. Moving on to talk about part B, assuming that A and B are sets of integers in the half-open interval, and again, this is an n, so you can't pick some specific value for n and only talk about what happens at that specific value. Given n log n algorithm. Now, the naive algorithm I was talking about before, where you use a couple of for loops, you're talking about something like n squared, because you're looping over possibly up to n values with a loop inside it that's looping over possibly up to n values. So the naive algorithm does not meet this requirement. But there certainly is an algorithm that will get you n log n. And I'll give people a couple more days to play with that idea, but we'll certainly make sure that you get an explanation in the Piazza forum if people struggle to actually get it. Which reminds me, I think we have some old small programming exercises that were assigned in previous semesters. We're not going to assign those formally, but I'm going to attempt to check into whether we can actually at least hand them to you in some form and say, you know, you can play with this as a way of convincing yourself that you understand what's going on. Okay, I'm being asked, does the half open interval imply that the set is continuous? And yeah, Trisha makes a good point here. When you say continuous in math, it usually implies that you're talking about real numbers, where there is no clear division between the numbers, like, you know, 2.999, 2.99999, 2.9999999. Most of this type of math is focused on what's called discrete numbers, which is, you know, for any given value, you know exactly what value comes next after it. There isn't always another value in between. But Dan did ask a very good question, that this does not imply that it has to be complete. If you look at the examples given, that example set B, 0, 1, 4, that skips some values. So it is certainly permissible to have sets that don't contain everything they could possibly contain. There is the lower limit of how many things it must contain is 1, because the problem guaranteed that the sets are non-empty. So something's got to be in there. And the upper limit is going to be n, because you can only start at 0 and stop at n minus 1. There are no more numbers available to use. But exactly how many any specific set is going to have isn't set. That was a terrible choice of word there. It isn't defined how many numbers are going to be in a specific set. They can take as many from the interval as they want, or leave out as many as they want, providing that they're at least non-empty. And just for the sake of talking about another equation for practice, this again means we have values of x that are found in the sum set, and this is just a pairing of x's and how many times you find those x's. This just turns it into a tuple. And so this particular set that it's describing you computing is a set of tuples. That's allowed to happen. Sets can kind of contain whatever, so long as you define them as being allowed to contain the thing that you say they're going to contain. In an abstract way, a set is just a collection of stuff that doesn't repeat. And I should add that there is no guarantee of ordering. I don't think it ends up really having an effect on runtime or anything like that. I mean, in a worst case scenario, you could say I'm inserting a step into my algorithm where I pre-sort them, and sorting is known to run in n log n. So the sorting itself isn't going to make things any worse than n log n unless you stick it in a loop or something like that. So you're free to say, I'm going to assume that my sets are ordered in advance if you're doing something where that's convenient, but um, it's not a terribly big deal here. There may be future problems where it could potentially become a big deal. I've seen problems in the past where it mattered, and that's why it popped into my head. So does everyone feel like they have at least a slightly better understanding of how to break down these equations and figure out what they're trying to tell you? I realize it took a slightly ridiculously long time talking about a couple of little equations, but I this is incredibly important. If you cannot read this stuff, then you can't read the problems, and you're kind of doomed before you start when it comes to the exam problems. I'm not sure why you're saying the lower bound would be n. Okay, anyway, there was one time last semester when a lot of people were misreading a particular problem, and I made a couple of videos where I walked through breaking down that specific problem. We could do something like that with the problem sets if people get really stuck on some, so that we can walk you through a bit. I try to do that rather than just say, oh, this is what the problem says, because I'm trying to show you how I'm thinking as I'm reading it to get to an understanding, rather than just handing you my understanding, because I would like you to be able to go on to future problems, and ideally, ultimately, you don't need me at all, and you can just do this stuff and say, oh yeah, that made perfect sense. I didn't have a problem there. So if there are specific problems where you feel like, wow, that is completely opaque, what the heck does that say? We could do some like mini contained videos on that and try to help people out. I will share it later. At this moment, I don't think it would make any sense because someone's asking if I could share the video from last semester. Um, Last semester, we did the computability and complexity stuff first, and then we did the algorithm stuff. This time, we're doing the algorithm stuff first and the computability and complexity later. So I did it early in the semester, but because of that, it's on material that you guys have never seen. And I don't think it would make any sense trying to read it. You would just be like, what are these concepts? I know sometimes people have asked in the past, do you recommend trying to do like 1,000 example problems quickly or working on 10 example problems really deeply? For the sake, particularly for the sake of knowing how to read a problem, if you go to a website like, Princeton's math classes or Berkeley's math classes or Stanford or whatever, that all run classes that are very similar to this and have a whole bunch of homework problems on dynamic programming and linear programming and fast Fourier transform and all of that, I think it would be worth your while to just say, I'm going to look at a bunch of these questions and just see if I can understand what the question is asking me to do and get some practice on that without putting a huge amount of time into it. But the thing about this is kind of the most transferable skill in the whole semester. Like if you understand how to read the math, it helps you on every single thing you ever do during the semester. There are other things like, how to conceptualize a dynamic programming problem that it's great to understand, and is certainly one of the things we want you to go away from the class with. But in terms of making it through the class, your ability to understand dynamic programming doesn't help you out that much when you're trying to prove that a problem is NP complete. Whereas your ability to read a problem correctly most certainly does continue to matter all the way through the class. So if you are stuck on this kind of skill frequently, practicing reading the problems, even without making yourself sit and say, okay, and now I'm going to also solve it, is not a terrible use of time. I say this over and over again, and I'm sure some people feel like I'm just lecturing them like they're little kids or something. And I feel bad about that because I don't want anyone to feel that way. But I've graded so many exams, and I have so many times cringed when I realized that someone completely misunderstood what we were trying to ask, and they turned the problem into something that I couldn't find a way to give them any credit for. Or in some cases, I might say, like, well, if I tilt my head and squint a little, I think I can give this a point. But there's no way to get beyond that because they just sent themselves off on a completely different line of reasoning that doesn't work out at all. And so I try very hard to save people from that when I can. I don't want you to have that experience, and both of losing points on a problem that you never got to make a legitimate attempt at, and of potentially losing points on other problems on the exam because you spent 45 minutes on this one where you were taking the completely wrong approach, where you could have spent some of that time on something else where you had a chance at getting some points. So that's kind of why I obsess over this topic. It's just, I've seen it hurt so many people. So many people. Good point. Sipser talks about set notation. If you do not have a copy of Sipser yet, his stuff is coming up in a few weeks. You could certainly, I would not necessarily recommend buying the Sipser book from a United States edition because we'll only be using it for like a month and a half, and it's incredibly expensive. Sipser 3rd edition is like $300 or something. The international edition is fine. The 2nd edition is fine. Renting it, I think Amazon will allow you to rent it for significantly less for a couple of months. That is fine. Sharing with a friend is fine. Please don't go on Piazza and share pirated PDFs. We don't like that. I'm not sure what all the legal elements are, but I think there's a strange situation involved if Georgia Tech classes start allowing pirated PDFs of textbooks to be shared in the official class forums. That seems like it goes to bad legal places. So if you do that, we will delete it or hide it or something. So please avoid that. But yes, renting should be fairly cheap. I'm not sure if you can rent an ebook for that one. There are other classes where you can. If you want the international edition, I would order it very soon because that, depending on where you buy it and when, sometimes those can take a few weeks to get to you. And international editions, in my experience and as far as I've heard, are basically equivalent to the United States editions, but they're printed on cheaper paper and they're not as pretty. Sometimes the diagrams aren't very nice and that kind of thing, but they get the job done and they do it for like 1/10 of the price. Hey, it's just over $200 right now. That's way better than last time I looked. But yeah, $232 is pretty brutal for a book you'll use for 5 or 6 weeks. Though, if you have some inkling that you might want to go on to more advanced math training and computability stuff, the SIPSR book is good. It is very short for how much it covers. It is incredibly dense in material. Once you start reading it, do not feel bad if you find yourself spending 20 minutes reading and understanding a paragraph. These things happen. But it is fairly understandable in general. Yeah. I believe CLRS is also available for free in electronic form through Georgia Tech. Like, I would have to look for the exact link, but I have it bookmarked somewhere. But Georgia Tech has a couple of sites where you can access ebooks like through their library, and you can get to some stuff like that. And there is also this is not as related to our class, but Georgia Tech has a O'Reilly Safari subscription. So if you're looking for books on like how to program kind of stuff, the way it was described to me during orientation when I got to campus, because we had a specific library orientation session, is that the school has a subscription that allows them to have 200 books available at a time. And anytime they put a book into that pool, I think it has to stay there for 30 days. But they're allowed to swap them as much as they want. So if there is an O'Reilly Safari book that you want, and they actually do have some theory stuff, I think, and some dynamic programming stuff and that kind of thing. If you want one of those books, you can actually send an email to the Georgia Tech library saying, I would really like to have access to this, but it's not currently on our list. Can you set it up for me? And they will often be able to honor those requests. So, if you're signing up for, say, advanced operating systems and you're terrified of C, but there's some great O'Reilly C programming book that Georgia Tech isn't making available yet, you can ask them for it. And there's a pretty good chance that they'll be able to make it available to you. So that's another option that you have. In addition, obviously you can go out and buy the books too if you want. But if there's something you'll just need for a few weeks and you think having access to the ebook would be nice, they seemed very eager to help, honestly. They gave the impression that they would really like it if people contacted them more often to tell them exactly what we want, because I guess they spend most of their time trying to guess at what we're going to want next, and it's always nicer to be absolutely certain that you've just made a change that's going to make people happy. Oh, if I don't know if that link is already on Piazza yet, Dan. Would you mind posting it? I this When this comes up on YouTube later, the comments feed doesn't end up being available, I think. So I would certainly like to make sure that anyone who hasn't seen that yet can get to it. Of course, if it's already on Piazza, that's good. I it's I've been in this class for like 6 semesters now, or 5 semesters. So it's really hard for me to remember if something was posted this semester or last semester or the semester before that. It's all getting foggy. Let's see, let's find something else we can talk about. Problem set 7 is a lot of fast Fourier transform stuff. I'm going to point out to Dr. Pryby that it might be nice to expand on the videos for that. Frankly, my understanding of fast Fourier transform is good enough to get through it when I'm trying to do a basic problem, but I'm not really good enough to teach it properly. And I couldn't block out like 10 hours to sort it out. Okay, thank you, Dan. So I didn't want to attempt to do that tonight. It would have taken too much time away from exam grading and that kind of thing. I personally, what I take away most from the fast Fourier transform part of the class is that even when you know a calculation is going to take a lot of time, sometimes you can make it fast by picking the input very intelligently. The videos spend a lot of time on things like exactly how it's executed, and it's good to understand that, but the coolest observation in there to me is, but wait a minute, we get to pick the values. So if I just use both x and negative x, then anytime the exponent is even, I'll get the same value there. And I can take advantage of that to make a whole lot of my calculations just kind of go away because I don't have to do it twice. I never really specifically asked, but that's always been my impression of why the fast Fourier transform stuff was in there. The original format of the class was like the first few weeks were on, let's talk about what a computer can do. And then the next few weeks would be, let's talk about things where we know the computer can do it, but how long is it going to take? Kind of like we know a computer can calculate its way through a chess game, but it's not going to happen anytime soon. So it's, as a practical matter, a complete solution of chess is out of reach. So that's what the complexity part of the class is. And then when you move beyond that, the reason we're talking about a lot of stuff like dynamic programming and linear programming and max flow is that we've already said a lot of these problems are really hard and they can take a lot of time. But if we take a really clever approach to them sometimes, we can make them a lot faster than we might have expected them to be. So that's what this kind of stuff is supposed to be supplying you with. Like string matching on its own is inherently a really difficult problem, but dynamic programming slices off a tremendous amount of time. The calculations behind doing the Fourier transforms there are a lot of calculations involved. But if you pick the values very carefully, you can get rid of a lot of those calculations and get an answer a lot faster. So it's sort of like the algorithms part of the course centers on almost often just ways you can avoid doing the calculations that would have taken you a lot of time. And I'm saying all this to try to provide some context because Dan was talking about this earlier in Slack, where he feels like nothing you do in this part of the class is strongly tied to the next thing you do. It's like dynamic programming and linear programming sound like they could be similar, but those are totally different things. And so no matter how much time you put in on mastering dynamic programming, it's not going to help you do better at the linear programming. And so I'm sure this part of the course probably feels very disjoint to you. Like, we're studying a completely different thing every week. What is up with that? I think in the old format of the course, it was easier to see that logic because we could actually say, we know this problem is NP complete, but we're going to attack it this way and get an answer faster. Whereas right now, it's hard for us to appeal to that reasoning because we haven't taught you about NP completeness yet. And so there's no really shared understanding among the class about what it means for a problem to be hard or why we'd be worried about taking such elaborate steps to build an answer. So hopefully that perhaps makes the content of the course make slightly more sense. The other way around, it was presented more as, okay, we are going to jump around and try a bunch of different things. And it was never really designed to make you a master of dynamic programming or anything like that. But I would say certainly the algorithms portion of the course will help you a lot more in things like programming interviews or for competitive programming. I have been told that dynamic programming is spectacularly important for competitive programming. Um, Apparently, it is relatively easy to come up with new problems that involve dynamic programming that in some subtle way. And so the competition people tend to take advantage of it very frequently. Um, the how to actually program stuff issues are more in the algorithms portion of the course. Later, it will be much more purely abstract, and we will talk about a much simplified way of modeling what happens during computation so that we can better talk about exactly how long something will take. Um, I, I know that for people who have a lot of practical experience, big O notation can be kind of bothersome at times, given that, theoretically this is what the algorithm does, but once you start thinking about the memory and the caching and where the bottlenecks are in the actual physical computer, there it is entirely possible that an algorithm that's theoretically better is in practical matters much worse. And frequently that is a source of frustration for people who are much more accustomed to thinking about the computer in a purely practical sense. Uh, this kind of material is more focused on, okay, what is in a perfect world where we didn't have to worry about that stuff, what is the best we could possibly do? So it doesn't come naturally to you, and I appreciate that. And I do my best to provide context when I can. Anyway, we theoretically are out of time, but we could flip through and talk about another thing. Let me see. I would say 8.1 is generally well covered by the videos. He walks through Ford Fulkerson. He does it on an actual graph. Some of those official videos have been edited to death and all the details taken out, but my feeling has been that Ford Fulkerson is one of the things that's better covered. It keeps more of its steps and they don't skip ahead quite so much on you. Let's see, number 2, I wouldn't think that would be so bad either. That is an interesting question. Dan is asking what sort of notation would work for representing this on a test. I would imagine if something like this were going to show up on a test, the graph we would use would probably be very small. I have never actually seen demonstrate Ford Fulkerson show up on a test. I think there have been multiple instructors for this class. I think the general feeling has been that this is more of a mechanical execution problem, and it's not really something to necessarily test. Um, I suppose you would do something like represent the nodes as tuples, like say, represent the edges as tuples, like saying, S comma C, and add some flow there, and CD add some flow there, and notate how much flow you're adding to each tuple. We've never really taught a notation that would be specific to this, so I would probably fall into the camp, like if this just popped up out of nowhere and I didn't see it in advance and now it's already on the test, I would probably say to the people grading it to be generous about how they figure notation because we never told you something specific to use. For actually doing this problem, I think it would make sense for you to figure out, like, walk yourself through Ford Fulkerson, figure out the max flow, figure out the minimum cut. If you compare those actual values to what the other students are getting and your values match, then you should be fine. Like, it's unlikely that you're going to do something extremely wrong but end up with the right value. So I wouldn't worry so much about double checking with the other students that you did like all the individual steps the same way. Let's see. If you're unfamiliar with this black box function, uh, if you're ever told that you can use something as a black box function, that means you don't have to worry about what's happening inside. It's like importing a class that someone else wrote in Python or even Java. Like, you've imported their class and you know that if I pass in this particular set of values, they promise they will give me back these other values and I don't have to worry about how they did it. That's the same thing. So what number 3 is saying is that you can say, oh, I'm going to assume that I have a black box function that executes Ford Fulkerson and will give me the max flow. And then from there, you don't have to talk at all about how the Ford Fulkerson is going to work or what exactly it's going to do. It's just a thing that happens for you. Let's see. Anything else that's likely to be confusing? I think number 4 is a good example of where it would be incredibly helpful to make notes for yourself as you're reading a question. Like, you know, M are the number of different disciplines. N is the number of tables that like pull out those little details so that you don't mix up what your variables mean. Because that problem is a lot less bad once you've broken it down, but when you're just trying to read it and it's just throwing different variable names at you, it's very easy to get confused. See, we haven't covered, I don't think this was covered at any length. Edge disjoint means they do not carry, they do not share any edges. When you're talking, the edges of a graph are held in a set, just like the sets we were talking about earlier. And anytime you're talking about two sets being disjoint, it means the sets don't share any members. So this is just a specific instance of the term disjoint, where it's saying we are specifically interested in paths where the set of edges involved are not shared at all. You will probably want to make sure that you understand the term disjoint, because I can't imagine we're going to get through the rest of the semester without seeing that again. The last time I did office hours, I talked about connected graphs. That essentially means that every vertex is in some way linked to every other vertex. So disconnect just means to take a connected graph and render it not connected. let's see, the edge connectivity of a tree is 1, and the edge connectivity of a cycle is 2. Uh, if you're not familiar with trees, they're the kind of graphs. We do binary trees an awful lot in CS where, we have a bunch of nodes that each branch off 2 different ways, and it just keeps on going down. And so it's saying the edge disconnectivity of a tree is 1 because if you were to just kill one edge, then this left side is no longer connected to the right side. So it's become a disconnected graph. A cycle is, I think we've actually talked about cycles, but a cycle is a set of connections where you can kind of go in a circle. And there it's just pointing out that if you were to only get rid of one of them, you'd still be connected because you have a connection going back in the other direction. So you have to get rid of 2 if you want to disconnect that. For number 6, I would say the most frequent misunderstanding for that was that people tried to solve it by just saying, we're tiling dominoes, so say clearly the first domino, some domino will have to go here because there's no way you can have a horizontal domino dealing with these 2 squares. And so then they would say, well, you can't be horizontal here in that case, so these 2 squares is also going to have a vertical. And then they'd kind of build out from there with a practical example, and this was not meant to be that kind of problem. This was meant to be something where you definitively prove mathematically. So doing that with the actual trying to tile the dominoes is good for intuition and good to show that you at least kind of read the problem correctly, but it's not the kind of proof that the problem is looking for. For full credit on that one, when it was actually, I think it was actually a test question. For full credit, people had to actually use some kind of graph theory or something of that sort to definitively prove that it was not possible for this to happen. Let's see, the concept of K-regular, I don't think that comes up a whole lot after max flow. But to cover it briefly, a vertex's degree is how many edges it has coming out of it. So like a little triangle graph, all of these vertexes have degree 2 because each one has 2 edges. And also, this is K-regular because all of their degrees are equal. So that's all that part is. This particular problem is a good example of induction coming up in odd places, because I would say, oops, the easiest way to handle part C is to attack it as an inductive proof. To say if I have a valid K-regular graph, I can remove one from each vertex that represents a perfect matching, and I will be left with a perfect matching. And that you can repeat this inductively, and it will always remain valid. Let's see. He's asking if there's a possibility to get more answers to the problem sets on Piazza. What we've been trying to do is make sure that every problem set question does eventually have a definitive answer, but what's happened in practice is that usually the definitive answer is provided by the students. That wasn't the original intention. Like the first time, the TAs actually wrote up their own solution. And then when I went back the second time to do mine, I was saying, some of them did a better job making it very clear than I did. So I think it makes more sense to say, oh yeah, that person did really good, than it does to try to provide another version of the same thing. But if that's not working well for people, that's a thing we can discuss. And just for the sake of pointing it out, there is often not a single right approach. I have, when the topic of things like cheating would come up on homework, people would often be like, how many possible different ways could there be to do it? And as a person who's actually read through 273 submissions of the same problem, it is amazing how much difference people can come up with. And usually the vast majority of the class will use an approach that was very similar to what we had in mind, which makes sense because it's somehow related to what you were just taught how to do. But there will also be people who come out of nowhere with something that we never dreamed of that actually works. And that's worth credit to. Why do the problem sets have more problems right after the exams? I think what's been happening is that the original schedule, we didn't leave enough time for a whole lot of time off. And so it's getting piled up a little bit in the week right after the exams. Okay. He's saying, in general, students would like to see a TA answer for the definitive solution, as well as an indication of the notation that might be used or expected on a test. We'll see how things are going. At the very least, we'll try to be more explicit that we're perfectly happy with what someone wrote. I mean, I have the problems that I have looked at least, the student solutions have generally been such that if I saw that on a test, I would be completely happy with it. Like, that is a full credit answer. So that was why it seems superfluous to try to rewrite it as another answer. I mean, there are always infinite ways to do it, though. In one case, it involved pseudocode, and it would have ended up being just about identical. But I'll talk to the TAs about that. We're finding that grading 5 exams takes up quite a bit of time, but we're figuring out how to make things work. It's a little hard in a class that we adapt every semester to try to improve it, because we can't just re-execute the approach that we used last semester for how to organize our time as well. So we sincerely try, and hopefully we are continuing to improve. I'm being asked how we decide how much time to give for exams. The original heuristic for this semester was okay, about half an hour of problem ought to be good. The fourth question was intended to be optional, so I think that was why additional time wasn't added for that. That ultimately comes down to, it's really Dr. Pryby who makes the final decision about how long a test should be. I don't think there's any particular science to it. In the past, exams were twice a semester, I think, and 8 questions in 3 hours, which was intense. But the assumption in the way the grading scale was built afterward was effectively that we know people aren't going to end up finishing every question. So there was a lot less time per question, but it was assumed that you wouldn't do them all. So the grading scale worked out such that it forgave people for either doing poorly on a couple of questions or skipping a few. Then later it became fewer questions with more of an assumption that you should be able to make some kind of credible attempt at all of them. And this semester we've gotten to the point where it's being treated as you should be able to handle a question in approximately 30 minutes. So I guess the how it's decided is kind of been an iterative process where we tweak it. Uh, it's hard to decide the right thing to do because in a sense I sort of liked having the fuzzy grading scale where we could adjust and say, well, yeah, but we knew they weren't going to finish all of it, so that's fine. We can just say 60% is an A. But that seemed to cause people a lot of anxiety. And we were trying to reduce the anxiety by bringing the scale of the test down into a level where finishing it should be somewhat more in reach. I believe the spring exams were more like 5 or 6 questions for 3 hours, though. So there were 3 hours, but you were doing more. Yeah, 6 questions sounds right. Um, let's see, there's only one problem left on this problem set. This number 8 was actually a bonus question, I believe, on a spring exam. And it's probably a very good example of something that doesn't take a whole lot of time if you have a good mental model for how matching works and how, what a graph should look like. Uh, I can remember when Dr. Pryby, he tested this problem on me to see how it was. And I think the core of the answer was like 5 minutes to get or 3 minutes or something. And then it would take longer to build out the proof and the explanation. But this isn't necessarily, it looks complicated, but it's not as complicated as it looks. So it's worth spending some time to understand it. But keep in mind that it was bonus at the time, or I think it wasn't really bonus, it was challenge. The grading scale at the time had problems that were designated as challenge, which you could completely skip and still get a B. And so it was considered to be one of the harder problems given. So if this ends up making no sense to you, that's probably not a disaster. But on the other hand, if you find yourself writing 3 pages of stuff about it, something has probably gone wrong. Because once you really understand it, it's not hugely complex. That's an interesting point. Someone's saying that a rule of thumb for exam length is that it should be 3 times the amount of time the instructor would require. I actually sincerely don't know how long it would take Dr. Pryby to do most of these problems. I know that I've occasionally come to him with questions and had him solve stuff in real time, ridiculously fast, frighteningly quickly. But I know there was also one fairly, I found it personally humorous. Someone turned something in last fall that turned out to hinge on some kind of really fine point of some definition for whether it was like completely right or just a really interesting effort. And I think 3 or 4 of us ended up discussing it for 2 hours. In the end, it turned out to be wrong. And then I was like, Well, I think if it took us that long to figure it out, we owe him some points anyway. Because clearly what this hinged on was so subtle that it's beyond what we should have expected him to be able to figure out. Okay, I guess we're officially 20 minutes past end time. I will see you guys on Piazza. We're scheduling more office hours. I'm There should be two more in the coming week, but I'm trying to figure it so that we're not scheduling them on top of when people are grading. Because if people have to take out a couple of hours to prepare for office hours and then an hour to do them, that's their entire grading time for the night probably. And then the time to get your grades returned gets pushed back another day. So we will have them scheduled, but I don't precisely know when yet. I believe I'm going to shoot for like sometime in the Wednesday to Friday range. And of course, you'll be able to just watch them on YouTube afterward. Um, don't think we have anything else that's imminent to worry about because we've just taken an exam. So there's nothing that's due right away. I'm sure there are people who are thinking about withdrawing or not. The withdrawal deadline is still a couple of weeks off. So there is time yet to make sure that you will definitively have the second exam grade back before then. I don't think it's terribly realistic to think that the third exam grade will be back by then, considering how things have been going. So 2 exams worth of grades will probably be where you are when you're deciding whether you want to withdraw or not. Otherwise, I don't think there's anything else we immediately need to talk about. So I will check up on Piazza, and thank you for coming and keeping me company and saving me from, totally talking to myself, because that would be kind of crazy. And it's extra crazy if you're just sitting around talking to yourself about math. So have a good night, everybody. Okay. The withdrawal date is October 29th, same day as third exam opens. For some reason, I had thought the third exam was the week prior to that. I must have mixed it up with an exam from another class. I have more classes to keep track of this semester than I've had in a very, very, very long time. So I haven't quite gotten the knack of keeping track of 6 classes at once again. Yeah, and thank you for your time, everybody, because you did take time to come keep me company.